Roya Kandalan, who is a senior machine learning researcher and an amazing woman-tech maker ambassador who wants to make AI accessible to all. And she just led two machine learning, professional machine learning engineer courses for New York and Boston. So I love working with her. Roya, you have the floor.
Thank you very much for the introduction. Thank you for having me. I really appreciate it. And we just listened to two very amazing talks by Peter and Alan. I personally learned a lot from them in my professional work. And I'm going to change the gear a little bit here to see how we can use AI for a different purpose. So here we are going to use AI for assistive navigation technologies to help people with visual impairment. So before we dive into the technicality of this work, let me introduce you to myself. My name is Roya, and it means a very sweet dream in Farsi. I was born and raised in Tehran, and then I moved to Dallas to continue with my grad studies under the supervision of Professor Kamishna Muduri. He is a well-known scientist in the field of unmanned airborne vehicle. After graduation, I moved to Boston, and currently I'm working as a senior research scientist at Aware, and we are working toward basically building a biometric solution that are free of bias and are impartial. I'm also a proud member of Women Tech Maker Ambassadors, and that's a program provided by Google to bring more women to STEM and to break the barriers that has been built historically for women to work, especially in STEM areas, because we are trying to hold each other hands and lift each other and grow with each other because we are stronger together. I'm also a co-organizer with GDG Cloud Boston. As Miss Anna mentioned, we are trying to provide more education to the community to bring AI and different technologies to everybody around us to make it really accessible for everybody. So without further ado, let's start with how it all began. As I mentioned, I'm from Iran and my advisor is from India. I want you to imagine yourself if you were in an area that you have, it is unknown to you, and your eyes are closed. I want to really try to get the fear that you might feel. The fear that you are feeling is exactly reasonable because vision is the most precise channel to gather information and reason in location. People who have visual impairment try to use other senses to collect the information that they require to have to basically understand where they are in their location. And assistive technologies can help them to essentially gain this information. But most of these assistive technologies and essentially the city structure that can help people with visual impairment navigate independently belongs to more developed country. When the person is in a basically more developing countries, some of these assistive technologies can be really expensive to get and sometimes they are not even available. Based on my background, I think I was more exposed to these sort of challenges. So with the help of my advisor, we were trying to build a technology that is not just a theoretical easy way for a smartphone, which is top of the line, but something really affordable that people who are maybe having some financial difficulty can also afford. So to build this technology, we require to answer few fundamental questions. So remember that we are trying to locate a person in an area. We want to know what is the best path for them to reach to their destination, and we need to make a decision about a map. In addition to that, given the difficulties and challenges of visual impairment, we require to know information about the occlusion and dangers in the area. On top of that, all of this information must be some way conveyed to the user. The initial design sketch that we came up with was, as you can see in this slide. The main core block of the system is a wayfinding module. It is responsible for finding the user initial location, interacting with the map, and also navigating the user to their destination. Given the user has visual difficulties, we want to gain some information about the dangers in their area and be able to pass all of this information compactly to the user. Okay. Breaking it down takes this problem into 3 different stages. The first stage would be the pathfinding. As I mentioned, for pathfinding, we need to know where the user is initially because they have no clue about their basically their initial location. Also, we want to be able to find the best path for this user to reach to their destination and to find the best set of actions to follow to reach to the destination. In addition to that, we need the second modulus obstacle avoidance to first detect the obstacle in the area and second, provide information about the relative location of this obstacle toward the user. Lastly, we want to first give the user a choice whether what extent of information they want to hear from us. And we want to be able to communicate the instruction about the actions that they must take to the user. And lastly, we want to be able to receive input from the user. So let's see, in this presentation, I'm trying to walk you through all of these stages and see how we can tackle each problem. But before we get into each of those problems, given that we had this constraint of budget, we require to know what is the best platform for this work. Again, because of the initial thought that we want to be helpful to people who might not have the financial means to get the best, basically a smartphone, we wanted this platform to be an accessible and affordable gadget. We wanted it to be able to do some minimal computation, and just for localization and other matter, we require to have internet connection. Given that we want to do localization and navigation, we wanted some inertial measurement unit or IMUs to be able to reason in location. At the time, we came to decide to use Samsung S7. This project started in 2016-2017. At that time, this phone only cost $120, which relatively was a small amount of money for a smartphone. It was able to handle Android Marshmallow with octa-core CPUs and a tiny GPU. It also basically supported VLAN and Bluetooth and had accelerometer and gyroscope. So all of the requirements that we had for this platform were basically satisfied by this phone. Now that we know the problem and we know where we want to go and what platform to build it upon, we are ready to basically dive into finding the best solution. The first piece of this puzzle was to find the initial location of the user. As I mentioned, we are thinking about a user who cannot reason in location. So they have no clue about where they are in their where they are located. Traditionally, people think about GPS or trilateration to reason about location. GPS signals are essentially satellite signal helping us to figure out where we are and how to get to the destination. However, GPS signals are not available in an indoor scenario. And trilateration are heavily prone to noise because of all type of basically signal to noise ratio issues and shadowing and bouncing and all of the problem that a signal can encounter when it's tried to transfer in an indoor area. Essentially, we cannot calculate geometrically where we are just by using trilateration. But all of this noise can actually come to our help. There is this other method called fingerprinting. By fingerprinting, we are trying to build basically a barcode for every location in an indoor area. When you are walking in an indoor area and your phone is connected to the Wi-Fi, you are constantly getting signal from all of the available Wi-Fi beacons. And your phone is measuring which one has the highest basically strength and tries to use that one to connect to the Wi-Fi. But you always get all of this information. So if you were to walk into the hallways and collect information about the strength of all of the beacons that are available to you, you can build something called a radio map, which is an association between the real map of the area and how much each of these Wi-Fi beacons have a strength in those locations. So you are building this signal strength map. It requires a lot of data collection, and data collection is always the most challenging part. The first part was me to go and walk through the area of my choice, which was the Department of Electrical Engineering at the University of North Texas, and annotate the map of the building with 1 feet a square. And then I needed to build an application to essentially have somebody walk through this 1 square meter location and tell me what is the beacon signal strength in each of those. That was the first time that I had to build an Android app. Thanks to Dan Golping, who is a Google Android developer advocate, and his amazing course on developing Android app, I built my first app for this data collection. The app would allow me or any user who would help me with data collection to enter the coordinate of XY coordinate of their location based on the annotation that I already made in the building. And it would collect all of the signal strength for all of the beacons that were available to me. By walking throughout these hallways 1,000 times and getting enough of information and some more data processing on this data, I was able to pass this information throughout a neural network and get the information about the XY coordinate of user location. At this point, I just checked one of the pieces of this puzzle. I could say I know where my user is when they are seeking my help. But the bulk of the problem is still there. I needed to know how I can get them from their initial location and take them to their destination, or quote unquote navigation. Traditionally, navigation is happening through pedestrian dead reckoning. It's a fancy way of saying that I know how much is my stride and which way I'm heading, and by putting one step after the other, I can tell where I'm going. However, this method is prone to error. There are two main sources of error. One is the compound error that happens because we are building the next step on top of the prior step. So if I have 1 degree of basically miscalculation in my first step and I take 100 step, instead of going to the north, I might just go to the south or something in that realm. The second problem is the measurement error. As I mentioned, on the phone, we have accelerometer and gyroscope. Accelerometer calculates acceleration for me. To get from acceleration to displacement, I have to integrate acceleration to get to the velocity and integrate over velocity to get to the displacement. It means that a tiny amount of error when it comes in acceleration can be a significant error when it comes to displacement. So it raised the need for some error mitigation method. The method that I used for that was particle filter. In 2016-2017, when I was working on this project, Google's self-driving car was the word of the mouth. And Dr. Sebastian Thurn, who was a faculty at Stanford, while he was working on this project, he had a course on basically navigation, and he would discuss different methods of removing the error with navigation, essentially. One of the interesting methods that he mentioned after the traditional method of, let's say, Kalman filter or extended Kalman filter was particle filter. The idea is that you basically have all of these particles, and based on the observation and measurement, each of them has a probability of continuing the progress. And by resampling and just choosing those that have the higher probability, you are removing those particles that can do something impossible. The simplest way of thinking about it is that it allows you to make sure that your user is not going to the second floor if you do not have enough of measurement to support that your user is passing through a staircase. Particle filter is amazing because it can handle basically non-Gaussian noise and non-linear system, which are the requirement for navigation in an indoor scenario. At this point, I was able to tell where my user is, and I was able to follow them along the path that they are taking using the sensors that were on the phone, and also using the error mitigation method to follow them along. I still needed to find the best path for them to reach to the destination. Right now, when you are driving and you use Google Maps, Google Map has this cost associated with you turning left being more costly than you turning right. So if it can find a path that allows you to turn right instead of a left, it tries to do that. To do that, there is an algorithm called A*star. A*star allows you to find the best path not only by putting it to be the shortest path, but to associate the cost with every decision that you are making. So here, because I was dealing with a visual impaired individual, it was important to me that I don't want them, for example, to pass a staircase. That's essentially a costly action. So A*star method would allow me to guide my user in the best possible and less costly path to get to their destination. With that being said, I had a technology to allow me figure out where my user is, what set of action they need to take to reach their destination. So it could be applicable to any person who is, for example, in a foreign country in an airport, and they want to find their basically destination gate. So they didn't know where they are and where they want to go, but they have vision to reason about the dangers in their area. However, a part of assumption for this work was that the user is visually impaired, so they do not have information about the obstacle in their area. For obstacle avoidance, I needed to be able to find these objects, find these quote-unquote obstacles, and estimate the relative location of this obstacle toward my user, and to be able to gain this information and pass it effectively to the user. Obviously, object detection comes to picture. For object detection, I use a YOLO, a TensorFlow version of YOLO, which was available on Google API. And I cannot talk about TensorFlow and not to mention Lawrence Monroy, whose courses on TensorFlow was really amazing for me in my professional career. I met him in person at I/O, and it was an amazing event for me. He has these TensorFlow courses, and basically it allows me to get the YOLO and do transfer learning to introduce all of the new objects that are not a part of YOLO package. For doing that, I use a Google Cloud Platform that allows me to take this model and retrain it just for a few top layers to introduce new objects. And thanks to Google, the first $300 was basically free credit. Also, in 2016-2017, we were introduced to TensorFlow Lite. It's an optimizer and wrapper for the neural network models that you create, essentially making it with a smaller number of bits, allowing you to get this gigantic model and make it so tiny that you can fit it on an Android device. It allowed me to have an obstacle avoidance module as well. But everything so far doesn't convey information to the user. So I required a way to be able to convey this information. I wanted the user to be able to tell me how much information they want to gain, whether they are on a run or they want to explore the area. I wanted them to be able to tell me where they want to get. And also I want to be able to pass all of this instruction to the user. To pass this information to the user, naturally I use Google Text-to-Speech. It would allow me to explain the options to the user and have them confirm some of the question that I had for the user. And also it would allow me to give instruction and tell them about the obstacle that they have. The more complex part of this puzzle is how to get feedback from user. The first thing that a developer could do was to use tapping. You always can have tapping on a screen of a phone as a way of receiving feedback from the user. I use it for emergency situation, for app to start, or for the user to tell me if they want to have some information right away. But it would have been impossible to finish this project if it wasn't for Google Speech Recognition API. For people who are familiar with the field, they know that building a speech recognition API is immensely difficult because the amount of annotated data that you require to cover the diversity of tone and accent it's so much that it's not possible for somebody to build. Thanks to Google Speech Recognition API, however, I was able to gain information from my user, so essentially take the information in a meaningful way and help them to declare their destination. With that being said, I was able to build a proof of concept for this technology, and I was able to show that with putting the right algorithm by side of each other, you can actually help a person with visual impairment to navigate in an indoor scenario independently. And at this point, I got graduated. But to take this problem, to take this project and technology and to really apply it in real world, two more problems must be tackled. First is when I was explaining the work, I explained that I had friends who were helping me with data collection to build a radio map. The radio map was the association between the signal strength from different Wi-Fi beacons and the location on the map. Practically, it's not possible to constantly update the radio map. And the radio map, because of the dynamic nature of the Wi-Fi beacons, going to be basically out of sync so quickly. So to be able to really build this project in a real life, we need some way of incentivizing people to help us to collect this data and constantly updating the radio map. We can use crowdsourcing essentially to have other people helping us with this updating. The second problem was in the initial problem I mentioned that in the fundamental problem I mentioned that the usage of a map is a question. And in the explanation I mentioned that I used a priori information about the map, and I knew I do have the map, but essentially if you want to use it for a new area, you can the map is not available. So there is this method called a structure from motion that helps you to take a few pictures and turn it to a 3D map and a 2D map to be able to use it for this project. With that being said, I'm pleased to say that I'm also part of a PhD committee member right now for people who are continuing this work at University of North Texas. Once again, thank you for being here and thank you for this opportunity. And I would be happy to answer any question. Thank you. Do we have questions?
Hey, Roya, that was awesome.
Hello. Thank you.
One question for you: do you happen to have um, your research paper and maybe the repo available for anybody who wants to play with or collaborate with you?
I do not have a repository for this, but my dissertation with all of the code is available, I think, on university website.
Awesome. And which chapter are you with? And do you want to tell a little bit about it, because you've been training a lot of our community on some of these technologies on a regular basis? You want to share
Yes,
that?
of course, I would love that. So I'm a part of GDG Cloud Boston, and we are trying to help. So I'm an ML scientist, obviously, and naturally, I tend to teach ML. We recently finished finished a certificate for Road to ML in Boston and New York, and I'm happy to announce that in late September we are starting a Road to TensorFlow certificate based on the book by Lawrence. So, yeah. Sorry, Alan, I cannot hear you.
Sorry about that. That was a great presentation. Thank you very much. I think one of the things that I had while watching you go through this are what were some of the biggest challenges that you faced as you were going through it, or what were some of the setbacks that you encountered, and how did you work past those?
So, to be honest with you, this project took me 4 years. So my whole PhD. Okay,
Wow.
I know. My whole PhD was working on this problem, and for each of these algorithms where they required for me a learning curve to get to them, to get to find the right algorithm to do the work, and also to be able to build this on an Android device. As I mentioned, the Android device that I was using was computationally not really powerful. So one thing that I vividly remember was to build the particle filter and to find what is the basically optimum number of particles that I could use to make sure that my user is still safe, but my device can handle the computation. There was basically a sweet spot to not to break the code and also not to lose the precision.
Wow. Okay. Thank you very much.
Thank you very much.